Chapter 12, Deflection of Beams and Shafts, example number 10. In this example, we do have a 1 degree indeterminate structure, as you can observe here. So there is a fixed support at A and a uniformly distributed load all over the beam, and at B we do have a simple support at B. So uh, for example, that would be a 1 degree indeterminacy for a structure, and that's why uh, we will talk about that. And we want to calculate RA, what RA is, what reaction at A is, what reaction at B is, and what is the deflection angle, what is the angle at B. Because theta at A is 0, there is no theta here, and there is a theta at B. We want to calculate these three parameters. Let's see how to approach this problem. So again, as I told you, this structure is 1 degree indeterminate. Mhm. And within the course of next 4 videos, we are going to solve this problem with 4 different approaches, which started in this video, which is 68, and the last three approaches in 69, 70, and 71. And it's a comprehensive example of a combination of solution for an indeterminate structure. Hope you enjoyed. Let's start a brief introduction. So long story short, solution one, it's a elastic curve equation from moment. So that's elastic curve equation from moment. So we cut the beam somewhere in the middle and develop the moment equation, and mm, and so on. From moment we integrate moment, then from moment we integrate theta and get the delta at last. And solution 2 is a considering moment at A as a redundant, because it's a 1 degree indeterminate. So if we just consider a, a ball beam like a two uh, consider of two beams like a two simple support beam at the left plus a two simple support, the effect of the fixed moment is a distributed is a concentrated moment at A. So we just translate the uh, fixed and the top beam to a, we just turn the fixed end at A to a two beam of a first a simple support, and then translate the fixed end by a moment at the again two simple support with no loading. So let's see, we'll solve it in approach 2, and yet we can solve it with a different approach, and that's a the effect of a superposition. We can uh, observe or investigate the effect of, for example, 10 different loading and compile them together with the effect of a superposition. So that's an addition of those separated effects on the structure. And the third approach is we can consider also RB as a redundant. So this time we just consider as if RB reaction at B is a redundant support. So again, it goes to a two different beam, like a cantilever beam, like a just take out reaction B, and you will have a cantilever beam with a distributed load of W all across the span, and plus a watt plus the same cantilever beam, but this time just handling a reaction upward reaction at support at the B. Mhm. So that's the third approach, and the last approach, which is the most, I think, interesting one. Again, we do have a superposition because we are adding separated effects and combining them with each other. And the last one is a work of an Italian engineer called Carlo Alberto Castigliano, which develops the Castigliano's theorem, and he was a mathematician and physicist in mid 19th century in Europe, which developed a his method by determining displacement of beams and shafts in a linear elastic system based on partial derivation from energy. So that's an interesting approach, which is our fourth method, and uh, we'll get back to it later on. Let's start the first solution. And again, Castigliano's theorem, for example, in a beam, it says if you define the energy by, for example, from a deflection in a beam, which is a flexural member, that's a U is equal to integration of 0 to L m squared effect of moment over 2 EI dx. And when you just derivate the energy function based on the appropriate kind of force, for example, if it's a vertical force, just go for vertical force. So that's a derivation of partial derivation of moment. So that's m squared over 2ei. It just turns to 2m over ei. So, and 2 with 2 cancel out, and then partial derivation of m over partial derivation of p dx. And that's a great approach and a huge uh, simplification in terms of many engineering problems. Let's start our uh, solution one. So in this method, which is a conventional method, which is a derivation of elastic curve or deflection equation from moment. So if we cut the beam through somewhere, for example, before the center or after the center, just by the length of x, and then we just develop the summation of moment about the point x goes 0, just considering the effect of external moment and also internal moment of ma, which is created due to distributed load. So that gives you a equation of moment, which is mx is equal to a negative w 1 over 2 wx squared plus rax minus ma, which both ra and ma are unknown. So what to do then? So we if we develop the equation of equilibrium for vertical direction, that gives us a two supports should cancel out the weight of distributed load. So Ra plus Rb just goes WL, and summation of moment about A should go 0, and it gives us the second condition, which is Ma is equal to half of WL squared minus Rb times L. That's if we call that equation number 2. And then 1 and 2, it just gives us mx, it just equal to a negative half of wx squared plus rax2 minus ma. We just replace ma on the equation. And if we call that equation 3, so if we integrate equation 3 two times, we can get the deflection from moment. So let's see how that goes. Ei theta, which is a slope, it's the first integration from moment, and the first constant appears here, C1. Mhm. And if we just and we call that equation 4, integrated once more, is it gives us the equation of a elastic curve, which is deflection, and we call that equation 5, and also the second integration constant appears. So If we apply the boundary condition to get the constant, uh, it just says at the beginning there is no theta, there is no delta due to fixed support, and at the end there is a no vertical uh, movement due to the support, ball support at the end. So in that sense, if we apply a and let's say a and 4, so if we put a, theta is equal to 0, and 4, which is equation for theta slope, it just simply gives us c1 equal to 0. Mhm. And that should accompany with a c1. Hmm? So that simply gives us c1 equal to 0 if you replace x by 0 in this equation, and the other one is just b. Let's go by a different color. Let's go by, for example, light green. B, which is this one, at x equal to 0, this time y is equal to 0, gives us c2, and 5 give us c2 equal to 0. So that's this one. If you replace all the x by 0 and you know c1 is 0, it just gives you c2 is equal to 0. Mhm. So by the additional uh, condition, which is at x equal to 0 all the way to the right, delta is equal to 0 again due to the support, and then c and 5. Mhm. Then c1 is equal to 0, c2 is equal to 0. It just gives us an equation which links ra with rb. Mhm. So if we just simplify that equation, it just gives us a equation of which is a what you can see here. Mhm. And let's talk about RA and RB from. If we just multiply that equation by a negative 6, it gives us the equation at to the right. Mhm. Gives us this equation by just multiplication at negative 6. Mhm. And at the same time, from the geometry of structure, we can easily know that RA plus RB are equal to are equal to, that's RB, are equal to WL, cancel the distributed load at the top. So if we just multiply this equation, equilibrium equation, we can get a set of equation to solve. So that just simply says RB is equal to 3 over 8 WL, RA is equal to 5/8, and that makes sense. That says R, that says RA take the bigger chunk of load in comparison. The fixed support goes by a bigger chunk of load in comparison to ball support, which is a 3 over 8. Then that's the 5 over 8 share goes for RA, and the rest, which is 3 over 8, goes by RB. Mhm. And then what if we just uh, go back to theta equation, and just for theta at B, or the angle at B, we just replace x by L, and if we just do that, do the math, it just gives us that theta B is equal to WL cubed over 48 EI, and that's theta B, which you can observe on the deformed beam, which is the elastic curve. Mm. And that just says theta B is equal to WL cubed over 48 EI. We'll solve this problem with that was the longest solution. We'll solve it with a moment area in terms of considering once MA is redundant and RA is redundant, and then with the Castigliano's theory in terms of calculation of the reactions, and also the angle of deflection. Thank you. See you on next videos.